So moving along, we're going to, whoops, sorry. I'm going to draw a couple of graphs and say where, in other words, on what interval is f 1 to 1. So here's the graph of the function. Okay, I'll just go ahead and label this point right here is, let's just say it's -2, 4. This right here is 0, 0. This right here is 2, -6. Let's call this 5, 0. And I can go ahead and label this one over here as, say, -3, 0. So here are a few points labeled down on this graph. Can you give me an interval on which it's 1 to 1? And remember, we had this theorem that said f is 1 to 1 on an interval if f is increasing or decreasing on that interval. In other words, can you find me some intervals where this function is increasing or find me intervals where it's decreasing? Sure. So f is 1 to 1 on the following intervals, all the way from -infinity up to -2. Because if I cut the graph off here, the function was just increasing, and where the function is increasing, it's 1 to 1. Or it's 1 to 1 from -2 all the way to 2, because here the function is decreasing. Or it's 1 to 1 from 2 all the way to infinity, because now it's increasing again. It's 1 to 1 on each one of these intervals, but it's not 1 to 1 overall. Okay? I can't start gluing together intervals where the function is 1 to 1 and expect it to keep that property. Because if I tried to, say, glue together all of these intervals, I would definitely start failing the horizontal line test. So it's perfectly fine for a function to be 1 to 1 on one interval, or to be 1 to 1 on another interval, but not be 1 to 1 overall. Okay. So why do we care about functions being 1 to 1? It has to do with the next definition, inverse functions. So if a function is 1 to 1, I have a way of saying, if I plug in something from the domain, I get out something from the range. How many ways could I get that out? If it's 1 to 1, there was only one way, which tells me if I know what I got out, I can actually determine what I put in. Because there was only one input corresponding to each output, if I know what I got out, I can say, oh, well, then I can figure out what I put in to get there. And that process of going from the output back to the input is called the inverse function. Okay, so if you have a function f and it is 1 to 1, it has an inverse function, which we use this exponent of -1. Notice this does not mean 1 over f of x. Okay, so it's possibly confusing notation because we're used to this exponent of -1 meaning 1 over, but in the language of functions, it means the inverse function. So f of x says input x, get out y. F inverse says if I put y in, I get out x. If I put in the correct output, I can return myself to the input that got me there. That's what inverse functions do. Okay, and there's a nice symmetry. If you have a graph of a function and you reflect it across the line y equals x, you can find the graph of the inverse function. So for example, look at the blue curve. Here's y is f of x. We draw the line y equals x, which is this nice diagonal line with slope 1. And then I start reflecting across this line. And how do I reflect across the line y equals x? You simply switch x and y. So if I had the point a1, b1, I reflect it to b1, a1. I just switch the two coordinates. a2, b2 gets reflected to b2, a2. We're just switching x and y, which is exactly what the inverse function does. The original function takes x and spits out y. The inverse function will take that y and return you back to x. It just reverses the role of what's the independent variable versus the dependent variable. It reverses the role of what you're putting in versus what you're getting out. It reverses the role of domain and range. So here's an example. Here's a function. It passes the horizontal line test, so it is 1-to-1. Can you draw the inverse function? And what you should do first is sketch the line y equals x. Notice the line y equals x goes through this point 2, 2. It also goes through the origin. So if I just sort of connect those with a line, it looks like this. So then what you do, well, theirs is slightly different, but you reflect it across that line, and you get this red curve that they've drawn here. So if you know the graph of f and it is 1-to-1, you can get the inverse by reflecting across the line y equals x. So I remarked just a minute ago, inverse functions swap the role of domain and range. So f takes an x and spits out a y. F inverse then goes the other way and takes y and returns you back to x. And remember, domain is what you plug in. So the domain of f inverse is what you got out from f. Whereas what you get out from f inverse, it returns you back to what you plugged in to f. So f inverse has exactly the reverse domain and range of f. So overall, let's see what happens. If you take an x from the domain of f, then I can apply f to it and I get out f of x. But now I have something in the range of f, because it's right there. It's f of something. It's in the range of f, which means it's in the domain of f inverse, which means I can apply f inverse. But if I got out f of x, sorry, my neighbor's dog likes to bark all day long. So if, yeah, there's 2 dogs. So if plugging in x produced this number f of x, which I can call y, what does f inverse do? If I plug that in, it returns me back to where I started, which was that original x. So f inverse and f, if I do the composition, I get out just x. And then this line, the second line, tells me it's really the same thing the other way around. If I did f inverse composed with f, I just get the overall function x. And what this tells me is if I started with x, then I applied f, and then I do f inverse. So I do f and then do it. What do I get back? Exactly what I started with. Sorry, this was the other order. Okay. So when you compose a function with its inverse, f inverse of f of x is just x. Nothing happens. Whatever x was, it remains x. And f of f inverse of x is the just x. Nothing happens. So let's do an example and verify that some things are inverse functions. In other words, compute g of g inverse and also compute g inverse of g, and what you should get is just x. And do the same thing for f in part B. So compute the compositions and see that you just get out an x. Okay, so I take g and I plug it into g inverse. Well, g was x to the 5th, but g inverse is written down as being the 5th root. What's the 5th root of x to the 5th? Just x. You can also do it the other way. Take g inverse, which was x, the 5th root of x, and plug it into g, which says raise that to the 5th, and what do you get? Just x. So no matter which way you compose the two, you just have an x at the end. That means they're inverse functions. So try to do that for part B with f of x, 4x minus 7, and f inverse given to you as a quarter times the quantity x plus 7. So f of x was 4x minus 7. Plug it into f inverse, which was 1/4 times the quantity input plus 7. The 7's cancel, and then the 4's cancel, and you just get x. The other way around, I would take 1/4 times the quantity x plus 7, and I'd plug it into f. But f said multiply the input by 4 and then subtract 7. So the 4 and the quarter cancel, and then the 7 and the minus 7 cancel. And again, you just get x. So because f of f inverse of x and f inverse of f of x were just x, these are indeed inverse functions of one another. Okay, so let's do another. Verify that these are inverses. For which values of x does this actually work out? So I'll pause here, try to go ahead and complete this. So The only issue compared to the previous examples is an issue of domain. Notice that the domain of the original function f is everything other than -2, but the domain of f inverse is everything other than 0. Now, if you do this composition, you take f of x and plug it into f inverse, we have 1 over x plus 2, which just means x plus 2, and then the 2's cancel and you just get x. But it's on the condition that x wasn't -2. Over here, it looks like x equals -2 looks okay. No, because back here, x equals -2 was not okay. Okay, because I wasn't in the domain of f, as long as x isn't -2, this all works out. But for x equals -2, that's not in the domain of f, nothing happens. If you do it the other way, take f inverse and plug it into f. Okay, now the 2's cancel and you have 1 over x, which is just x, but provided x wasn't 0, because 0 isn't in the domain of this part right here, 1 over x minus 2. They're still inverse functions of one another. It's just f inverse of f is x, provided you're in the domain of the composition overall. Okay, so back and we'll do more dealing with inverse functions, verifying inverse functions, but really what we need to get to in the next video is, suppose you just have a function f of x, how do you find the inverse function?